The moon was very close to the early Earth, and it receded as history has gone by, as time has gone by, and the oceans of the Earth were formed both by outgassing from the inner of the Earth, but also by comets and asteroids delivering materials to the Earth. So the early history of the Earth, between about 3.5 billion years and 4.5 billion years, was really tumultuous. There were huge impact events and massive, basically destructive events where the whole ocean could be turned into steam for a period of time and then recondense. But we have reasonably good evidence, although we don't know when the earliest forms of life began, we have reasonably good evidence that life began already here about the 20-yard line on our football field. So here we are at this point, and we know there's life forms because we still have similar cyanobacterial life forms called stromatolites that we can find in various places on the world. And these structures are solid and form incredibly good fossils. But the organisms that were inhabiting the early Earth were undoubtedly these tiny microorganisms that we now call bacteria or archaea. These organisms lived in a very peculiar environment because the atmosphere of the Earth in this early period of its history was mostly hydrogen and helium. The outgassing from volcanoes formed carbon monoxide, carbon dioxide, sulfur dioxide, sulfur, chlorine gas, nitrogen gas, and ammonia. And there was some methane in the early Earth's history. The atmosphere now, as we're breathing, is 78% nitrogen and 21% oxygen, and then the rest is in CO2 and a few other minor elements. But where did this oxygen come from? Because in the early Earth, the oxygen was less than 2%, maybe even less than 1% of the atmospheric gas. This oxygen was a pollutant from these organisms that were living in the early Earth, which were doing photosynthesis, which was taking the energy from the sun, breaking water, liberating oxygen, and using CO2, making their own biomass, making their own bodies, using CO2, water, and the energy from the sun. But liberating the oxygen into the atmosphere was a pollutant in the early Earth's history that accumulated and accumulated and accumulated until about the 45-yard line, the oxygen got to the point where it started rusting the minerals, the iron in the ocean, which precipitated out, and we formed what are called the iron-banded shales. About 1.6 billion years ago, which on this map is around the 35-meter line, 1.6 billion years ago, the Earth reached the atmosphere which it has more or less today, 78% nitrogen and about 21% oxygen. What you're noticing on this timeline so far is that the only organisms that we see are these microscopic bacterial and archaeal organisms, and indeed, the first life forms that arise that are multicellular don't show up until we get to about the 25 or 30-yard line. At the 30-meter line, about 1 to 1.4 billion years ago, we have evidence for the first multicellular life on Earth. Before that, it was all tiny microbes. But what's going on here? We're still in the really microscopic scale. It's important to realize that all the way down to the 13-meter line before the goal, which was about 500 million years ago, the Earth was not what we are familiar with. The continents were all together in what's called Pangea. All the continents which fit together were together, and there was a large ocean on the opposite side of the planet. And this is where, at that time, 13 meters from the goal, we were beginning to see the diversification of life on Earth, partly driven by that large accumulation of oxygen. This process, called the Cambrian explosion about 500 million years ago, led first to the jellyfish, and then we see plants arising at about the 10-yard line. Insects arrive about 8.4 meters from the goal, and we see amphibians rising about 8 meters from the goal. The dinosaurs show up at about 5 meters from the goal. The first dinosaurs start to appear. What is this like? Well, I showed you that the Earth was very different. All the continents were together during this period of time, about 300 to about 250 million years ago, a period in the Earth's history called the Permian. At the end of the Permian, when the continents started to separate, there was huge volcanoes, and these continents are breaking apart, and huge amounts of lava are released onto what is now called the Siberian Traps, and this generated massive amounts of carbon dioxide that went into our atmosphere and changed the atmosphere. So as the breakup of Pangaea, which was when the continents were all together, the supercontinent was called Pangaea, when this happened, the breakup was associated with this massive extinction where 90% of all families of life disappeared from the Earth. This went into what's called the Triassic from 250 to 200 million years ago, which on our football field was about 5.6 meters from the goal to about 4.4 meters from the goal. And the dinosaurs begin during the Triassic, but they actually expanded during the Jurassic. The Jurassic is a period of about 200 million years to about 146 million years ago, 4 meters to about 3 meters from our goal. And the key here is that the dinosaurs reigned for about 130 million years. They reigned all the way through the period called the Cretaceous, which ended 65 million years ago. And it ended with a bang. It ended with a massive impact from an asteroid or a meteorite that was probably about 70 kilometers in diameter and was traveling at about 17,000 kilometers per second. When this huge object hit the Earth, and we think that it hit around what's now in a region near the Yucatan Peninsula, it exploded and sent around the globe a layer of iridium that settled into the sediments, and we can map this incredible explosion that occurred at this period of time and wiped out the dinosaurs. That much energy would remove about 10 meters of seawater. It would turn to steam, and it would form rock vapor that would last for hours in the atmosphere. And by the way, these types of massive impacts occur on average about 100 times in the 4.5 billion years of the Earth's history. But most of the time, there were only microbes living on that Earth. So now, just to put everything in perspective, in the period of time we went through the Tertiary and the Quaternary, we're now at this distribution of continents, and the continents continue to move. So let's go back to our timeline. After the dinosaurs, which had reigned the Earth for 135 million years and disappear around 1.4 meters from the goal, we see the flowering plants arise. The flowering plants arrive about 3 meters from the goal, less than the width of this stage. Before that, there were no flowers. The flowers in our timeline become very abundant about 2 meters from the goal. Mammals are around at the time of the dinosaurs, but become very abundant somewhere around 1.4 meters from the goal. After the dinosaurs are wiped out, the mammals seem to take over. But hold on, where are we in this picture? Well, the earliest and most primitive forms of humans were probably Australopithecus africanensis. This organism was around between 3 and 4 million years ago, our ancestor. That puts this organism somewhere around 10 centimeters from the goal. But what about us? We arrive about 200,000 years ago, good evidence that modern Homo sapiens sapiens, about 200,000 years ago, that's 4 millimeters from the goal. So, if we think about the dominant organism on the planet, well, if we have to zoom in on that person's hand to be able to see those organisms, here's a single-celled yeast, and those are the microbes that have dominated the planet for 3.5 billion years. Now, there are still bacteria and archaea, these microscopic organisms dominating this planet. So no matter how many baths you take, about 10 times more bacterial cells on our bodies than there are human cells. And if you're familiar with the microbiome is about 100 times larger than our whole microgenome, than our whole human genome. Modern Homo sapien. We've been here for 4 millimeters of our timeline, about 200,000 years. How does this compare to the dinosaurs? Well, the dinosaurs were here for quite some time, 135 million years. And they got wiped out by an unfortunate accident for them, probably lucky for us. But let's look at something else. Let's look at 650,000 years of carbon dioxide in our atmosphere shown on this graph. And what you see here in parts per million is that the carbon dioxide went up and down, and when it came down and went back up, we would see the end of an ice age. And here it goes up and down, and an end of an ice age here when it goes up and down and up and down and up and down. Now, humans arrive on the scene here 200,000 years ago, about 4 millimeters from the goal. Our whole 650,000 year timeline is 1.4 centimeters long. The Industrial Revolution starts there, and where we are today is at about 400 parts per thousand. The first time in 650,000 years that the amount of CO2 in the atmosphere has been above 280 parts per million, or 300 parts per million. This is significant, and we're going to spend the rest of my talk this evening talking about this, but we need to put it in the context of the human experiment.